Hello everyone and welcome to lecture number 7 in calculus-based physics. Today we will be discussing gravitational potential energy, as well as the total mechanical energy of an object. We saw previously that any moving object has a special type of energy called kinetic energy. We will see today that any object above the surface of the Earth has a different type of energy called potential energy, and that the sum of the object's kinetic and potential energies are equal to the total mechanical energy. Let's get started. In order to understand potential energy, we must first discuss a new way of classifying forces. Before, we grouped forces into two categories, contact and long-range forces, and we saw that all long-range forces are called fundamental forces. Today, we're going to group forces into two new categories, conservative and non-conservative forces. So what are these new categories? I'll start by defining what these categories are, and then we'll dive into the details. A conservative force is any force that does no work when acting on an object as it traverses a closed path. A non-conservative force is simply anything that isn't a conservative force. In other words, any force that does do some work over a closed path. Now, our notion of what a closed path is critical in understanding these types of forces. So what do we mean by a closed path? A closed path is simply just any path taken from point A to point B and back to point A, as shown here. In other words, any path that starts and stops at the same position. This figure shows a few cases of closed paths. First, one could travel from point A to point B on the green path, then take the blue path back to point A. Or they could travel along the red path to point B and turn around and take the red path back to point A. Both options constitute a closed path. Let's take a look at an example of a conservative force. Consider a box thrown upward and moving under the influence of the gravitational force. As the box moves from its initial position, y1, to the maximum height of its trajectory, the displacement vector is pointed vertically upward. Recall that the displacement vector always points from the initial position to the final position of a moving object. Now, look at the vector for the gravitational force. It's pointed straight down toward the ground. We could, in theory, compute the work done by the gravitational force on the box as it moves upward from y1 to y2. If you think back to the previous lecture, any force that opposes the motion of an object, in other words, points in the opposite direction of the displacement, does negative work on that object. So, to summarize, the gravitational force does negative work on the object as it moves upward to its maximum height. Now, what about after it passes through the maximum point of its trajectory and starts moving back down from y2 to y1? In this case, the displacement vector points vertically downward. And if you look at the gravitational force, it too points vertically downward, as it always does. Therefore, on the way back down, the gravitational force acts in the same direction as the displacement, and so it does positive work on the box. So the gravitational force does negative work on the box on the way up, and positive work on the box on its way down. Also note that this box is moving on a closed path from y1 to y2 and back to y1. Therefore, gravity must be a conservative force. The work it does on the way up cancels out the work that it does on the way down. Before moving on, we should address an example of a non-conservative force. Consider a box sliding across a horizontal floor from point A to point B and back to point A on a closed path. From point A to point B, the displacement vector points to the right, whereas the kinetic frictional force points to the left, opposing the motion. Therefore, we can deduce that from point A to point B, the friction force does negative work. Now when the box is sliding from point B to point A, the displacement vector points to the left, whereas the friction force points to the right, again opposing the motion. This means that the friction force does negative work on both legs of the trip. It never cancels out over a closed path, like the case of the gravitational force. This is exactly the definition of a non-conservative force. In fact, all frictional forces are non-conservative forces. Let's take a closer look at the conservative case and put some equations to it. The work done on the box on the way down can be calculated using our definition for work. The magnitude of the weight times the magnitude of the displacement times the cosine of the angle between the weight and displacement vectors. But the angle between S and W is 0. They're pointing in the same direction, downward. Since the cosine of 0 is equal to 1, we can get rid of the cosine term. Plugging in mg for the weight and y2 minus y1 for the magnitude of the displacement vector, we get the following for our equation for the work done by gravity: mg times y2 minus y1. Now, in this situation, on the way down, our initial position was y2 and our final position was y1. So let's write the positions using initial and final like we usually do. Distributing the mg term, we get that the work is equal to mg y initial minus mg y final. These two terms are what we define as gravitational potential energy. The gravitational potential energy of an object is defined by mgh, where h is the height above some reference point, which is usually taken to be the surface of the Earth. Although the reference point, as always, is completely up to you. To denote gravitational potential energy, we used U sub g. And as with any type of energy, it has units of joules. Now, in the previous slide, we had calculated the work done by the gravitational force using this equation. But we can now rewrite it as the difference in gravitational potential energy between the initial and final points. Note that we need to include a minus sign because the delta is always final minus initial, and what we have in the equation is initial minus final. Note that this equation looks very similar to the work-energy theorem, which relates the total work done on an object to the object's change in kinetic energy. Now, let's make use of these two equations. We know that in general, an object can be acted upon by both conservative and non-conservative forces. So, the total work done on an object must be the sum of the work done by conservative forces and the work done by any non-conservative forces. Next, we know that gravity is a conservative force, so we can substitute the work done by gravity for the conservative work in the equation on the left. This gives us the following equation, which relates kinetic and potential energies. We can make this look a bit nicer by doing a little bit of algebra. First, let's get rid of the deltas by writing the kinetic and potential energies as final minus initial. Next, I'm going to get the non-conservative work alone on one side and group together my final and initial terms. Now before moving on, let's define our total mechanical energy as capital E. This is just the total amount of energy that an object has, which is just the sum of kinetic and potential energies. Then we can rewrite our equation above as work non-conservative equals the change in an object's total energy. This is an extremely famous equation called the conservation of energy. It's perhaps the most important equation, along with Newton's second law, that you'll learn this semester. Let's see what it tells us. We saw before that non-conservative forces are basically friction forces. Therefore, the equation that we just derived represents the conservation of energy in the presence of friction. The work done by non-conservative forces is simply just the work done by friction. It's this equation that describes what's going on when a creepy snow-covered guy rubs his hands together to warm up. As you rub your hands together, you are converting kinetic energy, the motion of your hands, to heat, which is another form of energy. The heat is represented by the work done by non-conservative forces in this equation. Now in this course, we often neglect friction. Not always, but often. If we neglect friction, the conservation of energy becomes a bit simpler. If there's no friction, there's no work done by non-conservative forces. Therefore, the conservation of energy looks like this. The initial total energy that an object has is equal to the final total energy for that object. In other words, the total energy of a system never changes. Now this is perfectly represented in the video shown below. Here we have a skier sliding down a frictionless incline. At the bottom of the incline is a horizontal patch of snow where friction is present. To the right, we have meters showing the amount of each type of energy. Initially, the skier is above the surface of the earth at some height and at rest. So the total energy of the skier is all gravitational potential energy. As they slide down, they speed up, which increases the kinetic energy. But the total energy stays the same because their gravitational potential energy is decreasing, because the height above the ground is decreasing. At the bottom, when they hit the patch with friction, they have all kinetic. Potential is zero because they're on the ground. Here, since friction always opposes the motion, it does negative work on the skier, and the kinetic energy decreases. What is happening here is that kinetic energy is getting converted into heating up the ground due to friction, just like the case of rubbing your hands together to warm up. Let's finish up by working through a couple examples. Suppose we have a ball of mass 5 kilograms and it's dropped from rest from a tall building 50 meters in height. In part A, neglecting air resistance, what is the speed of the ball on impact? In part B, if you measure the speed of the ball on impact to be 28 meters per second, what is the force of air resistance acting on the ball? If we'd like to find the speed of the ball at impact, we can simply utilize the conservation of energy in the absence of friction. EI equals EF. The total energy is made up of both kinetic and potential energies. Now we just need to identify which of these four terms applies to the problem. Take a second to think about which terms here might be equal to zero. Since the ball is initially at rest before being released, the initial kinetic energy must be zero. Likewise, the final position of the ball is on the ground, so the final gravitational potential energy must also be zero. Therefore, all of the gravitational potential energy the ball started with gets converted into kinetic energy at the bottom of the fall. Plugging in our equations for potential and kinetic energies, we get mg times the initial height of the ball equals 1/2 mv final squared, the velocity at the bottom of the fall. Here, masses cancel and we can solve for the final velocity. I get 31.3 meters per second for the final answer, but you should check my calculation. Now, what if in reality we measured the speed of the ball at impact to be 28 meters per second, not what we just calculated? That indicates that we didn't take air resistance into account, when we probably should have. So let's use another form of the conservation of energy in the presence of friction. On the right-hand side, we still have the same terms for the initial and final energies. Final kinetic energy minus the initial potential energy. And we can plug in the same equations for them. But how do we deal with the left-hand side? We just need to calculate the work done by friction, or air resistance in this case, using our equation for work. Looking at the ball as it falls, the force of air resistance is pointing in the opposite direction of our displacement. Therefore, the angle between them is 180 degrees, and since the cosine of 180 degrees is -1, we can just replace the cosine of theta by -1. Then we find that the non-conservative work is just the magnitude of the force of air resistance times the distance the ball has fallen through the air, with a minus sign. We can plug that into our left side of the equation. And rearranging, we find that the magnitude of the force of air resistance is 9.8 newtons. Note that this has nothing to do with 9.8 meters per second squared. It's just a coincidence that we got the same number as g. Before we look at another example, let's go back to our discussion of springs. Remember that when we stretch springs, the amount of work required is given by this equation, where k is the spring constant and x is the stretch or compression distance. Now it turns out that the spring force is another example of a conservative force. This means that we can write the work done by the spring force in terms of potential energy. This time, it's called the elastic potential energy and represents the amount of energy stored in a stretched or compressed spring. Mathematically, we define the elastic potential energy as 1/2 kx squared, where k again is the spring constant, x is the stretch or compression distance from its equilibrium length. So let's do one more example. This time we'll neglect air resistance. Here we have a 0.5 kilogram mass at rest on a compressed spring with spring constant 200 newtons per meter. When the spring is released, the mass is shot upwards. What is the maximum height reached by the mass above the top of the spring? And we're going to assume that the spring is compressed initially by 0.1 meter. Since we're neglecting friction and air resistance, we can use the simplified version of the conservation of energy, EI equals EF. But now we have three types of energy at play: kinetic energy, gravitational potential energy, and spring potential energy. The problem, however, works the same. We just need to identify which terms are present in the problem. Since the ball is initially at rest, the initial kinetic energy is 0. Likewise, when it reaches its maximum height, the ball is again at rest, so the final kinetic energy must also be 0. Now, initially, we have a compressed spring, so there must be some elastic potential energy. However, after the ball is launched, the spring is no longer compressed, so the final elastic potential energy must be zero. So this is the equation that describes the conservation of energy for this specific problem. Now we can plug in the appropriate equations for both elastic and gravitational potential energies. mgh initial plus 1/2 kx squared for the spring, and that must equal the final gravitational potential energy, mgh final. Now, in the picture, we've set our reference point, or 0 point, to be the end of the spring launcher. So what would be the initial height of the ball? Since it's initially below our reference point, the initial height would be negative 0.1 meter. Note that you can choose whatever reference point you'd like. You could choose the bottom of the launcher, but in this problem we weren't given the length of the launcher, which you would then need to know in order to solve this. Rearranging and solving for the maximum height, I get the following equation. The final height is equal to the initial height plus this tiny little factor, 1/2 k over mg x squared. Plugging in what we're given, I find that the final height is 1.9 meters. But again, make sure you check my algebra and calculations on your own.